So we finished up the last video by talking about how when we represent organic structures, we're really talking about where the electrons are, right? And we listed the four different areas where electrons could be, sigma bonds, pi bonds, lone pairs, and carbocations, right? These are the things that we're going to use to talk about how does reactivity occur in organic molecules, okay? And how does stability occur? When we talk about structures, we want to talk about, are they stable, are they unstable, and how do they react? And all of these things, sigma bonds, pi bonds, lone pairs, and carbocations, are the things that we're going to talk about when we start to talk about organic chemistry reactions. Now, we need to represent those, and so the next thing for us to talk about is going to be drawing organic molecules. And that's the topic of this video, and so we are going to jump right in. Drawing organic molecules. The good news about drawing organic molecules is basically it's just following the rules. And so we just need to set down what the rules are. So the rules for drawing organic molecules, there's kind of three simple ones, and then it kind of gets more complicated from there. The first thing, when we draw an organic molecule, we always represent carbons, carbon atoms, by corners or endpoints of lines. Right? So if we draw a structure, I lost my marker, there we go. If we draw a structure, everywhere that my line changes direction or ends represents a carbon. Right? And so you can look at this structure that I've just drawn and figure out how many carbons are involved in that structure. Second rule for drawing organic molecules, we don't draw carbon-hydrogen sigma bonds. Now, every carbon-hydrogen bond will be a sigma bond, because the nature of hydrogen is that it only can accept one bond at a time, and the first bond that we draw is always a sigma bond, right? And so every CH bond will be a sigma bond. And what we can, if we follow this rule, we can assume that every carbon, every neutral carbon, has four bonds, and any bonds not shown are CH bonds. Right? So when this structure that I drew earlier, right, this structure has a chemical formula of, whoops, C6H14. And so rather than having to draw out all 20 atoms of this structure in a Lewis dot structure kind of way, where you have to show where every pair of electrons is and where every atom and nucleus and everything is, we can just use lines to kind of show where they are, and it also implies where all the hydrogens are. Okay. So this is basically a way for us to simplify organic structure. The carbons are important because there's always going to be carbons in almost every organic molecule that we talk about, but we represent the carbons without necessarily writing a C in each position. Right? We represent the hydrogens by implying that they're there. The third rule is always draw heteroatom hydrogen bonds. Right? So in this case, we don't have any nitrogens or oxygens in there, but if we were to draw something like ethanol, we would have to have an OH there. And this is important for the formal charge things that we talked about before, because oxygen to hydrogen, we know that there's a sigma bond there. Oxygen to carbon, we have a sigma bond there. That means we have two lone pairs, and we can go back to our previous slide and see that oxygen in general has two sigma bonds and two lone pairs when it is neutral. So drawing in those hydrogens allows us to kind of catalog all of those all of those sigma bonds so that we can figure out the formal charge of heteroatoms. With carbon, that's not a problem because carbon is almost always going to be neutral and it's always going to have 4 bonds. Okay, so the simplest case for organic molecules are all sigma bonds and all carbon and hydrogen, right? So exactly like this idea up here, right? Nothing but sigma bonds. We have no pi bonds. We have no lone pairs. We have no carbocations, right? So it's all sigma bonds, and we only have to worry about carbons and hydrogens. These simple compounds, these are called alkanes. Um, so in this case, well, we've already kind of done this, can we find all 20 atoms that are a part of this molecule, right? So hopefully you've paused the video and made sure that this all made sense to you. But if I were to draw in all 20 atoms, you should pause the video now if you don't want to see how this works. Figure it out yourself and kind of place all of your hydrogens around this molecule. And notice that what I'm doing is we start at a carbon and we look at, okay, all the sigma bonds that are shown are other carbons. And then I know, so this carbon has 3 sigma bonds shown, so the 4th bond has to be a hydrogen. This carbon has 1 sigma bond shown, and so we add 3 more CH bonds to get to 4 in a neutral carbon. This one has 2 hydrogens, this one has 3. And if we add all this up, that should get us to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens, and 6 carbons. So we have all 20 atoms came here. Okay, so here's my challenge to you. Can you draw, before you start the next video, can you draw another structure with the molecular formula of C6H14? So draw a structure that's different from this one, but still has this molecular formula, and draw it in the line notation that we usually use, not showing the hydrogens and etc. And so we'll start off the next video with some examples of what those other compounds could be.